Thank you. Thank you. So good afternoon. Oh, it sounds like I'm yelling, doesn't it? Is that better? No, worse. I've just completely destroyed it as usual. Yeah, it's really good when theorists start playing with equipment. I mean, this is not mine. This is mine. I don't remember. No, this is not mine. I have one over there. There's too many bottles of water with too many different colors. So it's a real pleasure to be here. I haven't been to Bangalore for 28 years, I think. And so it looks exactly the same, which is nice because it's always nice to see that some things never change. And so thanks very much for inviting me. And I hope, since I have now two tough acts to follow, I'll do my best. And what I'm going to tell you is, first of all, let me just acknowledge that everything I'm going to talk about, well, more or less a little bit later when we talk about some results, which are not going to come today, are done with Paul Chaikin at NYU in New York, which has a much nicer view than the one you saw this morning, because it's uptown rather than downtown. And Stefano Martignani, who's our postdoc. And what I'm going to tell you about is basically the whole title of this work, of this school. So after my lectures, you just don't have to come anymore. And you may not want to anyway after these lectures. So I'm going to talk about order, organization, and information. And I don't think the word entropy isn't in there because I'll put it in later. Okay, but you could add it if you like. Okay, okay. So let me. So what I'm going to start off is, and I'm going to do half of this talk on the board and half of this talk showing pictures, because you have to somehow pass time. There's a really long. An hour and a half is a long time. And I don't have anything to say for an hour and a half, so I have to show pictures. So I'm going to give you some random thoughts which may be connected, right? So, I think maybe they're connected, and I'll leave it to you to decide whether they are or are not. They are, but I'll leave it to you to decide anyway. So the first thing is, what is order? And so I'm going to show you some artwork, because it's always nice. I don't know, I mean, in Israel, specialization is very early. In high school, students either decide they're going to study some sort of scientific discipline or some sort of liberal arts discipline. And I understand the same thing is true here, actually. And if you study liberal arts, you know no science. And if you study science, you know no liberal arts. And when you ask a question like, what is order? It's a really loaded question, right? Because you're going to have somebody who says, well, okay, let's see. I learned about phase transitions, and I have broken symmetries, so I can talk about that. Oh, really? Okay, that's true, but when that breaks down, what do you do? When you don't have a group, when you don't have a symmetry group, then you don't know what to do. So it's always good to go back to some things which one should have learned at some point, which for me is always just go look at art. Or listen to music. I mean, then somehow one gets some ideas. So this is a painting by the American artist Barnett Newman. It's in the Museum of Modern Art, as are basically all the pictures I'm going to show. It's called The Wild, and it's from 1950. And when I was a kid, I would have said, this is not art, this is crap, right? I mean, I could do it. And so therefore it's not art. Actually, Barnett Newman even has a whole white canvas, which was too complicated to put up. So I mean, and as I've gotten older, I sort of have more of an appreciation for the difficulty it is in making these things, and then having the idea to do it, and to be fearless enough in the face of many critics, like my 12-year-old self, who of course knew everything wonderfully well, who could then pass judgment on these sort of things. So this is Barnett Newman, 1950. Okay? This is Mark Rothko, another guy I thought was just a real hack. 1949, it's called number 3, number 13. So the name is interesting. It's, it's sort of, so he's got, this is typical of all of Rothko's paintings. Horizontal lines, all of the late Rothko paintings, horizontal lines of color, and it's quite different from the Newman, but nonetheless, there's certainly a sense in which this is well. I mean, physicists would like this because it's sort of like. Here's Pete Mondrian, which is even the reductio ad absurdum of the previous. I mean, so this is just a bunch of primary colors with some black lines. This is a later Mondrian, and since we already heard about Broadway, so this is the Broadway Boogie Woogie from 1942 to 1943 by Mondrian. It was, so it's also really very regular. So I've shown you a bunch of regular things, and so here's Jackson Pollock by contrast. So this is Jackson Pollock, and it looks like any 5-year-old could do this. Looks more like any 5-year-old has done this, right? And gotten royally chastised by his or her parents, right? Because you can't clean the rug now, right? So this is Jackson Pollock, 1950, and here's a much more famous Jackson Pollock, number 31, also 1950, and the technique here is to take paint in brushes, the way you might paint a wall, and throw it and drizzle it onto, this is a rather large canvas. Okay, this is not quite as long as this blackboard, but it goes roughly from here to here. It's a fairly large thing. So you could say, well, the hard part was not to step on it as you're doing it. But in point of fact, this is. I mean, I love Jackson Pollock. It's just that it's so easy to criticize this sort of thing, and it's. Pardon me? Oh, he may have stepped on it. I don't think so. I've seen him. I've seen the footage of this being painted, and it doesn't look like it. So, but my point, aside from just lulling you, trying to put you to sleep, using the criterion that when 50% are asleep, the talk ends, is to just make a distinction between what at least I would say are far more ordered works of art and the Jackson Pollock, which I would say are far less ordered. You could do this in music as well. You could play some counterpoint from the late 17th century. You could play some Bach, and then you could play Alban Berg, if you know this guy who seemed to dislike pianos and would then beat at them. So you could make the same sort of argument, or if you're making an argument at all, that there's some sense in which your eye and your brain picks out something which you would say this is more ordered, this is simpler than this other thing. Okay, that's the point I want to make. And what I want to go do in these lectures is to ask whether I can actually make that precise. Not only whether I can make it precise, but whether I can actually quantify it. And if I can, do we as physicists care at all, or am I just talking about art poorly? Right? So that's going to be the point of the talk. So the question is, can we identify order? Now I have and/or simplicity. I'm going to come back to those points. So that's what I want to know: is can we identify it? And it's a loaded question because it's difficult. You look at something and it's hard to say that this is ordered and this is not ordered. Maybe you could say if there's some sort of a process that the system is somehow ordering or not. If a system is crystallizing, let's say, from a fluid, then you might say, but there's your broken symmetry again. You might say it's becoming more ordered as it crystallizes, if you like. But there's your broken symmetry again. I want to tackle harder problems than where I know the answer because of a broken symmetry. But sometimes it's really easy. Here the symmetry is broken. You have this very regular honeycomb pattern. Any physicist would say this is ordered, right? It's a crystal if you want to think about it as a physical system. And here's another example which is slightly more complicated. This is a Penrose tiling. It's made up of two tiles. It's non-periodic. It's so-called quasi-periodic, which means it has Bragg peaks in its diffraction spectrum as a crystal does, but it's also very ordered, very regular. So if I use the word regular instead of ordered, then you say, yeah, this is regular. The crystal is more regular. And if I use them interchangeably, I'd say the crystal is more ordered. This is less ordered. But is there a way I can make that idea more precise? Now, those guys are fairly easily said to be ordered. But then I have things like this, which are a little bit more. I don't know if I guess I don't have a pointer. Do I have a pointer in? This is a pointer? Yes. So I would argue, well, this particular cellular structure reminds one maybe of a foam, maybe not. This thing looks to be more ordered than this one does. And going down the line, I mean, between here and here, I don't really know what to say. So I could, if I make it a comparison, I'd say, yeah, this thing looks somehow more ordered than this one does. But what I'm really picking out in that case is the fact that the area of the cells is roughly uniform, and here it's not. That's really what I'm picking out. That's okay. But as I say, so that was the prelude to the sometimes it's not quite so trivial. For example, if I have a soap froth in 2 dimensions, would I say this is ordered or not ordered? I mean, I'm not going to say. What I can do is I can watch the evolution of a soap froth in 2 dimensions, as was done here, starting from what they call monodisperse. It's not quite monodisperse, but nonetheless it's fairly regular. If it were monodisperse, it would have to be a hexagonal lattice, which is not a perfect one, but it's still pretty regular. After some time, you get the state evolving to this sort of a structure. The reason that these guys have not evolved is because they were really they made a very good honeycomb lattice, and in two-dimensional foams, honeycomb lattices don't evolve in time. But ultimately, these guys which grow eat these portions away, and I come to something which is typically called the scaling state, what people believe to be a steady state foam. So I could ask the question, this is meant to be the same system. As time goes by, does my system order, disorder, or neither? I mean, and so I can ask the question. Whether I can answer it is another issue indeed. But I want to suggest to you, at some point or other, probably not today, that the answer is yes. And here are a couple of pictures which are even harder, right? These are non-overlapping disks in 2 dimensions, about 36% area fraction, which means that the dark portion that you see is 36% of the total. These are. I'm not going to tell you what these two processes are, but I think I can ask the question. I mean, it's pretty difficult to see which one is more ordered, if it's even meaningful to ask that question. My point here is that it's difficult. If it's even meaningful to ask, it's a hard thing to answer. I don't have a nice broken symmetry to rely on, or anything else. Nothing here is regular. So is this more ordered than that? I mean, I think there's an answer to the question, but which I'm not going to give you just now. Maybe I'll come back to it. But I would say that it's a hard problem in any case. And one's intuition takes you so far and no further. And here's another example to that effect. I mean, again, these are 2 different. I'm not going to tell you really where these come from either right now, but these are the same density, and they came from different processes, and it's the same sort of question. Can I say that this is more ordered than that? Is there a meaning? Is there a meaning to ask the question? And is there a way of answering the question in either in more than just some sort of a wishy-washy way? Is there a way of actually making some quantitative, giving some quantitative measure? That's the question, and that's what I want to address in the lectures I have here. And here's another pretty picture. This is a computer simulation of a chicken eye. So you could ask whether that's regular. It sort of seems like it's sort of regular. It's so-called hyperuniform, which if I have time, I'll come back to. But it's not ordered. There's no crystallinity to this. So can I, in any sense, give some teeth to the notion that such an image is ordered? And if so, what's that? Yeah. How was it simulated? I don't know. Sal Torquato simulated. I don't know how he simulated it, actually. Truth of the matter is. So what if Sal's students did it? Well, yeah, it can. And so the question is, can we bring some? So Chandan asked whether the way you think about order can vary. Is it a personal thing? We like one type of music, we don't like another type of music, and we don't necessarily agree. But is there a way in which we can actually make this precise enough that you'd have a hard time disagreeing? Okay, that's what I'm going to try to do. We'll see if I succeed. Okay, so here are the questions that I want to ask, and what I want to see if I can answer, at least in part. So the real question is, can we assess the extent of ordering? Can we identify order? Can we quantify it? That's what I should have written. And more specifically, if the answer is yes, then what are we trying to get out? What would I like to be able to say? Because we're physicists after all, and in the end we have to actually do something. So what I'd like to say would be, I'd be happy if we could get out of this sort of treatment is something about timescales for systems which self-organize, which are out of equilibrium or self-assemble. I would like to have some idea whether I can make some sort of a statement about timescales, even if, as I showed you, the system is organizing or self-organizing in a way that's difficult to pick out by eye, or even to define an order parameter which would help you to quantify that. So the first thing I'd say, well, how about timescales? Can I see the way in which a system organizes in time? Can I identify where phase transitions occur? And can I discuss their nature? Now, if you're in thermal equilibrium, life is easy because it's already been done for you. In thermal equilibrium, you have a critical point, and you measure your thermodynamic functions. You see where you have some sort of singularity, and according to what function has a singularity, you classify the phase transition as first order, second order, continuous, whatever it is you'd like to do. And we'd like to be able to do that for equilibrium, but it's already been done, so you won't get very many points for doing that. On the other hand, there are systems out of equilibrium which have phase transitions which are considerably less clear than those in equilibrium, and those are the ones I'd really like to ask questions about, because those are the ones I don't know the answer to. Can we measure the scales over which a system is correlated? Again, if I have a system in equilibrium, I coarse grain, I identify an order parameter, usually by looking at the low temperature phase, identifying the order and the broken symmetry in the problem, and define an order parameter and ask about the correlation of that order parameter. That works just fine, assuming that I'm in equilibrium and assuming that I know what the order parameter is, which I don't always. So for systems where I don't have that machinery, can I make statements about correlation lengths? Can I understand divergences of various quantities. Do things diverge at all? For example, in systems which are not in equilibrium at phase transitions. We know, for example, the correlation length diverges at equilibrium critical points at phase transitions, second order phase transitions, continuous phase transitions, and various other derived quantities. Can I make some sort of statement about systems out of equilibrium? And can I understand a little bit about the nature of self-organization problems and their extent? And so the question that I want to ask about all these things, these are a bunch of goals I might set out for myself. And the question I really have to ask is how we can do this in principle. And if I can do it in principle, is it practically useful? In other words, I can propose to measure something, but it may not be measurable. So that would be just wonderful. It will be the thing theorists do best, right? How many folks here want to do theory? Okay. How many want to do experiment? And how many are just wishing they could exit without me seeing? The rest of you who don't raise your hand. So experimentalists do real things, and theorists sort of talk around real things sometimes. If we're really close to experiment. So I want to know whether I can make some sort of a theoretical framework, and I don't want to stop there. I want to ask whether it's useful. Okay, and I think that's all I want for. No. Okay, so okay. I started. So I showed you some pictures, some artwork. I went a little bit to physics. It's too much physics right after lunch. So I'm going to change gears for a second. Okay, and here's a question. Okay, here's a question. What's the next number in the sequence? 7207843. Anybody? I'll give you like 20 minutes. Oh, I don't know either, right? But fortunately, there are a lot of people who have nothing to do, right? And they all go to this website, it turns out, right? I'm not going to ask how many of you know about this website. I didn't, people are acknowledging it anyway, which is gutsy. I didn't know it existed, okay? I was just looking, okay? So the answer, according to this guy who's a game developer at Render Ideas, and he's a Bengali, so that's great for Chandan until I tell him he got the wrong answer. No, I mean, so he goes and he has all these, and maybe, you don't have to bother reading this because you don't really care, but the answer is 11, which is obvious when you look at it, right? I mean, what else could it be? 720784311. Okay, that's really great. Well, but that's one answer, right? And most of the people got this answer. This would have won, this would have won the election. 11 would have won the election. But there were some other answers, right? 10 was an answer, but I forgot to copy that. Here's one. The sequence is clearly approximated by the polynomial. This is not a Bengali. From which it follows the next element is 42. All right? This is the deep learning, right? This is the deep learning method. Okay? Where we exactly, okay? So this is, this is just great. And you sort of, in your mind's eye, you imagine we're in Ramanujan building, right? And you sort of imagine this guy calculates by hand. The answer to every question is 42, right? Yeah, I do know, but that's okay. Okay, very good. I didn't check to see whether this is true. I confess that maybe this is just, but okay, but that's good enough. He's a PhD student in theoretical nuclear physics, and as you all know, nuclear physics is dead. So this is the only thing they have going for them at this point. So therefore, this is probably legit, right? It's legit. Sorry? Yeah, this is also on Quora. Yeah. Yeah, I spent like 5 minutes of my life on this website. But this guy, Don Engelmeyer, says the answer is irrelevant, useless, and a waste of time. And the only question you have is, what were you doing on Quora? Because this is the right answer, obviously, right? This is the right answer. All right. I think this is where I want to. Okay. So the point is that this is ill-defined, but I'll just do a little more of this. The point is that this is an ill-defined question, and to make it a little bit more clear, I'm going to ask a stupid question. What is the next number in the sequence 1, 3, 5? Okay. I'm not going to give you 20 minutes to do this one, right? Because everybody here, everyone, is going to get the wrong answer and say 7, right? I mean, obviously it's 7, right? Odd numbers. So that's so, and I write down. Yeah, you can write down an equation for this, right? A of n is 2n minus 1. That's really cool. So clearly the right answer is 7. I'm bringing this up because when I was a kid, and you would get these problems, and I'd usually get them wrong because I basically got almost everything wrong. So I could, and they ask, what's the next in the sequence? I always thought it was a stupid question because I can always guess. I mean, you give me 3 numbers in a sequence. So here's an answer. What's wrong with 8? All right. Okay. An is the sum from 1 to n of the floor function. That's the floor function of x is the greatest integer less than x. Okay. That's what this thing indicates over here. This means the greatest integer less than the argument. And indeed, if you calculate it, a of 1 is 1. A of 2 is the floor function 2 over 1, which is just 2, plus 1 is 3. A of 3 is floor of 3, which is 3. Floor of 3 halves, which is 1. And floor of 1, which is 1. That gives me 5, so that's cool. And A of 4, if you work it out, turns out to be 8. So, which is the right answer? Well, I mean, they're both the right answers, and, but there's a point in bringing this up. Right? There's a point. So my question really is not what's the right answer, because that's a silly question, but whether there's a sense in which I can say that one is simpler than the other. Okay? And in that sense, to say this is a better answer. This is an Occam's razor sort of question. Okay? Is there a better answer even though they're both correct? Right? And better, it may be better is the wrong thing to say, but maybe simpler is okay because I can't really quantify better, but maybe I can quantify simpler. Okay? I can quantify simpler. Okay, but I can't quantify better. So is an equals 2n minus 1 simpler than an equals the sum of the floor functions? I don't know, maybe yes, maybe no, I don't know. I mean, I don't know at this stage anyway. Okay, so can we quantify what we mean by simplicity? And what I'm really thinking of is not sequences of numbers that you might have gotten in elementary school when there was clearly a right answer, right? There was clearly a right answer. But I'm really trying to get to the question of whether ordered states, in particular, many body states out of equilibrium. So there will be physics in this, but it's going to take a while to get there. Okay, but that's where I'm going. Are ordered states simpler than disordered states? Because if we can find a way of defining simple or quantifying simple, does that give us a sense in which we can quantify order, even when it's not quite so obvious as, let's say, a hexagonal lattice or a square lattice or whatever other lattice you like, versus a random array of points? That's what we're trying to do. Okay? We're trying to get at those subtle questions, not the obvious ones. The subtle ones where I showed you a bunch of pictures and I asked you which one is more ordered, and honestly, you can't. You can't say. Okay? Okay. And this gives us the notion of what's called, so let's make it precise now. This is really beautiful. Okay, this is just really, really gorgeous. The notion of Kolmogorov complexity, which was developed by Kolmogorov and Chaitin in 1965. So Andrei Kolmogorov was a great mathematician. I'm sure you've heard of him. Various remarkable things. I think he was the one who did the who did the turbulence, fully developed turbulence, which is just a thing of absolute beauty. And this is unbelievably beautiful to me. And Chaitan, just to make you guys feel bad, okay? The paper written in 1965, you look up Gregory Chaitan, it's published in some journal or other, I forget which, offhand. And you usually look, it says Chandan Dasgupta, Indian Institute of Science, Malleshwaram, Bangalore, India. Okay? Well, you look for this thing and Chaitan doesn't have a byline. You say, well, what's going on, right? This guy must have been somewhere, right? He was an undergraduate. He was an undergraduate when he did this. And so if you want to be depressed, there are things you can do. There are various ways. There's another guy, I'll tell you this, you can be depressed twice today. Okay, this is the first time. The second time will come a little bit later. Okay, so what these guys said was the following. They defined a notion called the Kolmogorov complexity. And what it says the following. It's defined as follows. It's the shortest computer, and I'm being imprecise and I'm being colloquial, and that's fine. These are mathematicians. They couch these in terms of Turing machines and universal computation and stuff like that. We don't really need to do that. The difference is translation, really. It doesn't matter what language you're talking about, really. They said that the Kolmogorov complexity of some object, which might be a line of text, string of numbers, it could be the photograph of you folks, anything you like. It's in the end, if I have a file, I can write it as some string, right? In the end, I have to do that. And the Kolmogorov complexity is the length of the shortest computer program which will produce that specific object as its output. Okay? So, if I give you a random string of numbers, it's not the length of the shortest program which can produce a string of random numbers. It's the shortest computer program which can produce that specific string of numbers that I gave you. Okay? So it's not as though you can just write something dumb and I say, oh, it's just generated something random, so therefore I did a great job. No, you didn't. You actually have to generate the one I gave you. The length of the shortest program which can produce the specific data that I gave you. That's the Kolmogorov complexity. Okay? So if I were to want to go back to the silly question I asked about what is the right continuation of the string 1, 3, 5, is it 7 or is it 8? I would say, is it shorter to write down the algorithm or the functional form a(n equals 2n minus 1, or a(n equals the sum from 1 to n of the floor function of n over j, which would take me less, could I program more concisely? And that I would say, following this, is the simpler one. Yeah. Pardon? Yeah, really what you don't want to have is 1, 3. You're always going to get into issues when the thing is very, very short. I would really have to, tell you something which is, no, it does not have to predict anything. But all these things really have meaning in the system when the systems are comparatively large. Thermodynamic limit is great, but even meso is all right as well. But you're quite right. I mean, if you say 1, 2, yeah.
So the shortest here is memory or time?
The shortest is neither memory nor time in the sense you're running a computer program. The shortest is the length of the program you have to write. Right? You type in a program which will produce this particular output. How many lines is it, or more precisely, how many characters is it? Okay, I don't care how long it takes to run. It can take forever to run. That doesn't bother me. Okay? Yeah. I mean, strictly speaking, what you have to do is, so that's where you've already invoked a higher command. Really, you have to write this for a Turing machine, and if you write it for a Turing machine, then you can't just take tailor-made commands which somebody has written. I mean, and those would go into the. So yeah. I mean, it's overhead. It's a constant overhead. The definition of that is constant overhead, but it's relevant. Okay, but it's relevant. Okay. So that's the definition of the Kolmogorov of complexity, and I just think it's absolutely gorgeous. To me, it's a thing of absolute beauty. I'm going to contrast it with another thing of absolute beauty quite soon, which is very, very different, but it turns out to be very similar, which is just remarkable. And as I write, I mean, this is basically how you would make a statement about Occam's razor, which theory is better. The simpler theory is the better theory, let's say. But without a notion of simplicity, that's an empty statement. I mean, again, unless it's obvious, right? So when I want to look at some simple objects, and for simplicity's sake, I like to use words simple in this slide. Let's look at some things in one dimension, because one-dimensional objects are easy, and I want to look at sequences of zeros and ones, 2 letters, only because it's simple. I don't have to do that. We could do things in higher dimensions. We could do things which take on with a larger alphabet than 0 and 1. We could do all that sort of stuff, but there's no real reason to do it at this stage, so it's after lunch and all this sort of stuff. And so here's a quick and dirty thing which I did with Jorge Kurchan some years ago, and that's to say, let me look at the number of patterns that I have and count them. Patterns of a certain size. I'll give you some examples in a moment. So if my size is L, so think about, if I'm thinking a string of zeros and ones, then words of length of L characters or N characters, how many are there? Right? That sort of thing. And I can ask how far do I have to go until I find exactly my neighborhood, on average, etc. So for something periodic, I'll show you in a second. Something periodic, it turns out that irrespective of the size of the word that you're looking at, the number of words you get is a constant. But I want to give you some, as I said, things which are periodic and things which are quasi-periodic. There are other means of understanding. So I want to give you some. I want to ask. First question is there anything to look at anyway? Is there anything out there which is not trivially accessible by conventional means? If the answer is no, then there's no real reason to do anything, right? It's already done. Okay, so let me look at substitutional sequences. I'm going to do this fast because it's not the main point of the talk. And it's the sequences of letters or numbers which are constructed recursively. So letters in this case are 0 and 1, as I said, and I want to construct them recursively with the following rule. If I give you a portion of a sequence, and everywhere I see a 0, I replace it with a 0 and 0, 1, and everywhere I see a 1, I replace it with a 0, 1. And if I do that, if I started, let's say, from 0 or 1, I get a periodic sequence. Life is very boring. It's just periodic, and the number of words of length n it's 2, but it's around 1. It's a constant. It doesn't really matter if it's right. Okay. That's not interesting, because I know how to tell if something is a crystal. I just do scattering, right? I look at X-ray scattering, or I look at electron scattering, or whatever it is, neutron scattering, and I see sharp peaks. I see Bragg peaks, right? So I don't need to tell you that's ordered, right? I mean, we already know that for quite a long time. Okay, what if I go 0 to 1 and 1 goes to 0, 1? All right, so that gives me something which looks like this, but this happens to be a very famous sequence. It's called the Fibonacci sequence, which is what underlines the Penrose tiling. And if I were to count the number of words of length n, it is approximately n. In fact, it's exactly equal to n plus 1, if you really care. It's exactly equal to n plus 1. Okay? So there are more words in the of given length in the quasi-periodic guy than in the in the periodic guy, fine. But those are things which we already know about, and the question is, are the things that we don't know about? And so, as I said, this was done with Jorge Kurchan. These ideas, Jorge is going to be here next week, as I understand. So, okay, we understand what ordering means in those two cases. I don't care about those. And if there's nothing else, then, as I said, then there are other means of ascertaining order. So here's another example. Here's 0 goes to 0, 1, 1 goes to 1, 0. I get something which looks like that. And this is called the THUE-MORSE, the THUE-MORSE sequence. It's neither periodic nor quasi-periodic. It's something called singular continuous. Whoop. Hello. There we go. Okay, that's singular continuous. Well, there you go. But it also has the number of words and letters is also scales as n. It's some number times n. So that's more complicated. It doesn't have Bragg peaks. So I don't know whether I'd call it ordered or disordered. It's certainly regular. I mean, I would argue that it's ordered. But all these substitutional sequences is pretty trivial to show. Have a number of words which is linear in the length of the word plus a constant. That's a white lie, but it's a white lie which I'm willing to make because I can make it precise a little bit later if you really care. It's a great book by Alush and Charlotte on automatic sequences where all this stuff is done very wonderfully. Yes. Well, I mean, so you know, strictly speaking, if what these folks, if you were to look at the way these guys talk, mathematicians, they say this is the limiting word, the infinite word. Okay? So, as physicists, we'd say, start with a 0 and see where it goes. Right? And you'd get to a finite portion of the infinite word. Okay, but it's a fixed point. It's the fixed point of they look at the fixed point of the transformation. So, you know, so we said, let's define order to be when that quantity, omega of n, the number of words, scales more slowly than exponential, because in exponential sequence, if I took just coin flips, Bernoulli sequence, then the number of words of length n, in that case, is 2 to the n, right? So it's exponential. I've shown you a bunch of power law, right? N, A times n plus B, or just a constant for crystals. So I say, okay, maybe that's ordered. We call that sub-extensive patch entropy. And here's one more example, which is called the Rudin-Shapiro sequence, which I hope I have. Yeah, here we go. It's a 4-letter sequence. It does this. The details aren't particularly important, but if I regard these 1s and 0s as Ising spins, where 1, let's say, is up and 0 is down, plus minus 1, let's say, if I do that, then, so I guess, so like that, if I look at that, then the Fourier spectrum, the thing which was telling us order about the periodic and the quasi-periodic case, okay, tells you that this guy is not only a continuous function, but it's absolutely flat. It's absolutely flat, just like you would get for a random sequence of coin flips. Okay? And yet, it doesn't have what I said a second ago, the number of words diverging as 2 to the power n, right? It just goes, the number of words goes as 8n minus 8. So I would argue this is ordered, but you would never see that from the Fourier spectrum. Okay, that's just sort of to make, we don't need that. And this I don't need to show you because I already showed you. That's just to give you a sense that there are things, there are things in this world, Horatio, right, that are not dreamt of in your philosophy. That there are things that you might reasonably argue as being ordered, which aren't the sort of things that you've already seen in physics. Okay, and because as physicists you ought to be open to the fact these guys might exist, and I could go give a series of lectures on that alone. you sort of would like to have a way of seeing whether that's what you're seeing or whether it's all garbage, right? Is the fact that you get a flat scattering amplitude indicative of order or of just junk, right? And if you don't ask the question, then you don't care. Okay, so I've already showed these things. And all of these guys have very small Kolmogorov complexity. So let me just give you a couple of examples. See, the problem with the Kolmogorov complexity, coming back to it, was that although it's very beautiful, it's a very beautiful construct, it's a gorgeous idea, it's practically useless. I mean, unless you want to prove theorems. You want to prove theorems, it's very useful. Okay? For proving theorems, it's useful. But for physics, it's absolutely and totally useless because you don't know how to compute the Kolmogorov complexity for anything except something like a random sequence. Okay? Because for example, a random coin toss sequence, plus and minus 1, the shortest program that I can write to get that specific sequence is print the following sequence and give you a sequence, right? And if it's plus or minus 1, each one is 1 bit. A bit is a unit of binary choice. So if I have a sequence of length n that I've given you, it takes n bits plus whatever you have to code to write print the following sequence, right? Which doesn't matter. It's just ballast, right? So there we sort of understand. So the Kolmogorov complexity in this case scales as the length of the string you're giving it. So that we know how to do. That's fine. Do I have? Yeah. I mean, I could say, well, what about print? Suppose that my sequence is 1, 1, 1, 1, 1, 1, 1 n times. Then I would just say print the number 1 n times. And if the computer knew a priori what n was, then that would be a really short program, right? It would just say print 1 and it understands the n. If you have to tell it the n, then you have to give it the n. But how many characters do I need to specify n? How does it scale with n? What's the great thing about we write numbers, right? It's exponential notation, sort of. Is that what scientific notation? Whatever. It's written as in exponents, right? So I need the log of the number, right? Bits of information in order to write that number n. Okay? So to print, so if I need to tell the computer how many ones to write out, then that the Kolmogorov complexity of that would be log n plus the ballast of saying print blah blah blah. Okay, which doesn't matter because it's independent of n. Okay, so for those examples were pretty cool. But if I give you something else, so you can come and say, well, how about this, doing it this way or doing it that way? I mean, who knows maybe we could compare and we could say this is better than that, but maybe lurking out behind there somewhere is something better. So we don't ever know what the best is because finding the best is not something you know how to do. So you can get some sort of a hopeful approximation, but you can't do better than that. And so the Kolmogorov complexity is a beautiful thing, and it's a great thing to think about, to focus on when you're developing ideas. But if you want to calculate something, it's utter rubbish, right? That's the way it is sometimes, right? Still, it's amazing when you do beautiful. Yeah, so it's just not useful for physics. So here's another thing. This is the Shannon entropy. So since this is an entropy conference, so the Shannon entropy. This was these ideas were formulated by Claude Shannon in the 1940s, and of course he knew statistical mechanics. Okay, and what Shannon was interested in doing was he was an electrical engineer or mathematician, whatever it is, he was anything he wanted to be. He was interested in questions of sending messages on transmission lines. These are things which are really important because everybody here, I think, has a cell phone, right? And you know, when you watch YouTube videos, because lectures like me are boring, right? As you sit and watch YouTube videos, there's no way, right, without the ideas of Claude Chandan, that you'd be watching these YouTube videos, right? Or doing anything else, right? Somehow there has to be, you have to find an efficient way of transmitting these messages. And that's going to be a serious point of what I'm going to talk about in the next couple of days. And so what Chandan he said the following. So I'm being precise here. Sometimes it's good to be precise. The Chandan entropy of a random variable x. So I don't know whether you folks have had probability theory. I'm not going to rely on heavy probability theory, but probability distributions and such like, I hope you know. So if I have a random variable, which I'll call x, with a probability mass function, this is math speak, p of x, the likelihood of drawing x is p of x, okay? It's a normalized distribution, it normalizes to 1. Then the Chandan entropy of that random variable is defined in the fashion I've written down over there as minus the sum over all possible values, all possible outcomes of that random variable, minus the sum of p log p, and I've taken the log as they do in the electrical engineering convention to be log base 2, because binary numbers are useful. Okay. So okay, this you presumably have seen this sort of thing in a stat-mech course, right? It looks very much like what you'd write down. Let's say if you're thinking about the entropy for an ensemble, which is not the, you could even do it for the microcanonical, but you wouldn't typically do it for the canonical, the grand canonical ensembles, right? So clearly he knew statistical mechanics, but I'm gonna talk about it in a way which is very different from the way that you have talked about entropy in your stat-mech course. So here it is. Okay, it's a measure of the average uncertainty of x. Okay? It's not a measure of disorder or any such other hokey things which people for some reason like to say. Okay, it's a measure of the average uncertainty of x. That's perfectly fine. And it's also the number of bits. It's binary 0, 1. Okay, choice. Number of bits on average required to describe x. And here I'm going to make this precise in a moment. Okay? So I'm going to try to give you a little bit of intuition now. Okay. But before I do, the amazing thing is that the Kolmogorov complexity and the Chandan entropy are really very closely related. Okay, and this is why the Kolmogorov way of thinking about information theory and the Chandan way of thinking about information theory are complementary. Chandan requires probability distributions. Kolmogorov requires an algorithm for generating an outcome. Okay, so how do you guys together? Comes from probability distribution. Let me draw from that probability distribution n times, concatenate the results. Okay, that gives me a sequence, which could be a sequence of ones and zeros. It could be a sequence of pictures. It could be a sequence of microstates from the Ising model. It could be lots of different things. Okay? Then if I take that concatenated string now x again, that could be each x can be a fairly complicated object, right? We don't care. The concatenated string from x1 to xn is a string which you can describe, which you can, in principle, compute the Kolmogorov complexity for, right? Shortest program which will give me that string. I don't know how to do it, but in principle I can talk about it, right? And if I could do that, I divide by the length of the string, number of characters in the string, or number of objects in the string, take that limit to infinity, thermodynamic limits again, and that's equal to the Chandan entropy. That's pretty remarkable, right? So I've got two ways of thinking about a problem which are really very, very different. Chandan says I need to know the probability distribution, and then I can compute the entropy. Kolmogorov says what I need to know is to look and see how complicated a string is. And these are complementary. Okay? Yeah. Well, if it's well, but you got to be careful, right? Because I mean, because I don't know how to do that, right? And the reason I don't know how to do that is because, I mean, it's comparatively simple if I know if my distribution is flat, right? Then it's comparatively simple. Otherwise, it's not. That's where things get a bit hairy. What's the Komorga? I mean, of a it's not. Of a quasi-random number generator, right? Well, I don't know the answer to that question because I don't know what the shortest way of generating the, right? I mean, you can define it. I understand what I'm talking. Look, I didn't prove this, right? I mean, I wish I had proved this. This is a theorem which I don't know how to prove, as a matter of fact. I'm just giving the, okay? I mean, there's a parallel way of doing all of information theory using Shannon ideas or Kolmogorov ideas. You can do it one way or the other, and it's exactly equivalent. But how you show that this is actually the case? I mean, it doesn't seem completely insane, but I wouldn't have guessed, obviously. But again, but you prove things around it. You don't actually compute it, right? That's the okay. So as I say, what does this have to do with physics, right? And the reason what's the problem, right? If you have, we have a process or some sort of a model which generates microstates. And if it's in statistical equilibrium, you understand what the ensembles are, you understand what the microstates are, you understand what the probabilities are in principle, and you're okay. And in equilibrium, the Shannon entropy reduces exactly to the ordinary thermodynamic entropy, they said. I mean, up to definitions of log or natural log or not. So that's just a factor. In front of that, it doesn't make any difference, and the Boltzmann constant, which also we don't care about, right? So that means that the Shannon entropy has meaning in statistical mechanics, in thermal systems, okay? And it's the regular entropy. So again, I'm going to go outside of so there's nothing I have to say about thermal equilibrium which you don't already know or will know when you take the appropriate course. So there's nothing, shouldn't say anything about that sort of thing. I mean, I know what the probabilities are of a state. In the canonical ensemble, it's e to the minus beta energy of the state divided by the partition function. That was given to me by God or Boltzmann, and that's all of thermal equilibrium. Yeah. I don't know. As I say, the only thing, you don't know how to compute the Kolmogorov entropy of anything, complexity of anything but the two examples I gave, pretty much, right? So that's a very, very white lie. I mean, there really is almost nothing else. Okay. So the Shannon entropy is, I'm going to make the point, again, the Shannon entropy reduces to the Boltzmann entropy in equilibrium, and we know that the entropy is important in equilibrium. So you might ask, reasonably, is the Shannon entropy useful in systems out of equilibrium? What's the problem? The problem is, well, okay. I mean, so two possibilities. Here's my binary thing. Yeah. No, it's garbage. Two, it's amazing. It does everything we want, right? Or one, it's not useful. Two, it is useful. So let's be optimistic, right? Let's say, yeah, it's useful. Okay? And then you say, well, hold on a second. I understand how to compute the entropy in thermal equilibrium because I know what the probabilities are. I just wrote them down, right? E to the minus beta E over Z. That's okay, or whatever ensemble you want to do, just change that. Out of equilibrium, we don't know the probabilities, so I can't compute the Shannon entropy. So maybe it's useful, but I don't know how to use it. I don't know how to, okay? So we've decided optimistically that it's useful, and unfortunately, we can't use it because we don't know how to use it. So yeah, it would be great, right? It would be great if we could fly. It would be great if we could fly, right? Right? Everybody agrees with that, I think. It would be wonderful. Unfortunately, we don't have wings. And for all of you who want to understand why we don't have wings, okay, I recommend that you read an amazingly beautiful essay by Haldane, not Duncan, right? J.B.S. Haldane, who spent most of his life in India, called On Being the Right Size. You folks know this? You guys, because you guys are more or less cultured. But for the ones who aren't cultured, okay, (1938), I believe. If you haven't read it, you should really leave now and read it because it's much more important than what I have to say. Right? It may be the most beautiful bit of scientific writing certainly I've ever seen. And it's remarkable. And it will tell you why angels don't exist. Okay? So I don't know so much the Hindu pantheon to know whether angels exist. But the Christians are really not doing very well because of this. And Jews believe in anti-grav, so it's okay. Right? There we go. Okay. So the question is, you know, we've speculated that the Shannon entropy is really, really useful, but we don't know the probability distribution. So can we approximate it? That's the question, and that's the point I want to. That's what I want to now talk about. And I want to use the word. So now we have to talk about coding. Okay. So coming back to information theory. So first, some examples. Just compute the Shannon entropy, and I'm going to come back to these examples in a moment. So let's just compute the Shannon entropy for if let's say x is integers uniformly distributed between 1 and 64. If you like, x is a variable which takes on 64 values with a flat probability distribution. Okay, everyone has same microcanonical probability distribution. Then the Shannon entropy is minus p log 2 of p is minus 64 times, well, p is 1 over 64, right, times the log of 1 over 64, and that comes out to 6 bits. Okay? These Shannon entropy is measured in bits because of log 2. Okay? And this is trivial, as you know. And we'll return to this later. Suppose I have an unfair roulette wheel where the probabilities are given like, I mean, I didn't know what the actual markings on a roulette wheel are. And I do know that they have more than 8 possibilities. Okay? So I just in a boring physics way, I wrote them as x1 to x8. And they have the probabilities listed, a half, a quarter, an eighth, 16th, and 1/64 for the last 4. Suppose this is my roulette wheel. Okay? What's the Shannon entropy of this random process of spinning the roulette wheel? Okay? Well, you go through the higher math and you discover that it's 2 bits. Okay? It's a calculation that you can do in your own privacy of your own home. Okay? So here's the question. You know the answer to this one. I shouldn't have shown the answer. Suppose I'm thinking of an integer. So I told this. I told this to a stat mech class that I taught, I don't know, 10 years ago, more than 10 years ago. And I said, look, I played a little game with my daughter, who was at the time, so it's probably like 14 years, she was 4. Okay? So I played this game with my daughter. No, she's 19 now. Jesus. And this is taped? Shit. Oh, God. Yeah, it's more or less what she thinks anyway. I mean, She was either 4 or 5. I don't know what the year that I did this. So I'm telling my students, and I'm saying, suppose I play this game with my daughter, and I say I'm thinking about a number between 1 and 64. All right? And guess the number, right? And she tries, and I say, then I will do it the other way, and I'll guess yours, and we'll play for money. Okay? I say she's getting money from her mother, right? And I just got divorced. And so I'm telling this to my class, right? Because I'm sort of out of my mind. And the students thought I was serious. This is the way I rip off my daughter, right? My 4 or 5-year-old daughter. And this is how I get even with my ex-wife, right? This is how I get all the money back, right? That really shocked me, that people don't have a sense of humor, right? I don't know if I can still say that in America, right? Yeah, I can't say that. For lots of reasons, I'm not sure why. But so many reasons, probably. But I can say it here, right? And it's on tape, and that means I'll never get a job in the States. Okay, so the question is, I'm thinking of a number between 1 and 64. I have no bias. What's your best strategy on average of guessing the right number? So everybody here is going to say, as fortunately you haven't done it, yeah, you just say, okay, is it greater than or less than 32? Right? I mean, anybody want to disagree that the way to do it is to divide the possibilities in half, right? And I'm saying yes or no, right? So you say, is it greater than 32? I say yes. So then, okay, fine. Then you say, well, what about is greater than 48? I think is the midpoint, right? I keep on dividing until right? And the number of questions I have, I mean, is I got to ask if it's 64. It's what is it? It's too hard for me. 6 questions? 6 questions. All right? And then I guess that. Okay. So that's easy, right? That's easy. And I did it between 1 and 8 because I want to make a point in a second. And the point I want to make is, suppose now that I tell you, look, I've got a fetish. I really like odd numbers, but I'm going to say a little bit different, right? I mean, there's certain numbers I like better than others. That's the way I am. Okay? But I'll tell you what I like. I'm going to still choose randomly, but I'm going to tell you what my preference is. So I just took my roulette wheel example, right? So I'm going to tell you that I like the number 1 probability to half. That means half the time I'm going to guess that. And number 6, I'll guess if we do this, n times 1/64th of the time on average, I'll choose that number. What's your best strategy now? Okay, it's no longer so trivial. It's still not hard, right? So what are you going to do is, well, I mean, a good guess anyway, is we divide the groups which remain, which I haven't ruled out by saying no, into groups of equal probability, right? So in this case, I'll say, well, the first question will be, is it 1? Because 1 has probability half, and everything else has the probability half taken together. So I'll say, I mean, is it 1? And if the answer is yes, I've gotten it. If the answer is no, or you've gotten it, and if no, you say, is it 2? Because 2 had a probability of quarter, and the rest together had a probability of quarter. Because that's the way I set up the example. Okay? So this seems reasonable. Seems like a reasonable strategy. So here's my guess tree. Right? Here's my tree. I start up at the top, and I say, is it 1? And so this 1 over here is the guess. Okay, this is what it means. When I write a 1, it means is it 1 or whatever it is. If it's yes, then that's the answer. If it's no, I continue. Is it 2? Yes, I guess 2, and everything is fine. No, I continue. Is it 3? Is it 4? Is it then I have 4 possibilities of equal likelihood, 1/64 each one, and I say, is it 5 or 6? That's equivalent to saying, is it greater than 32? Is it 5 or 6? If the answer is yes, et cetera, et cetera. That's my strategy, okay? That's my strategy. That seems like a pretty good strategy, right? Seems like a pretty good strategy, right? I want to show you that's the best strategy. So how do I show you it's the best strategy? There are various ways of doing it, but I want to show you it's the best strategy by giving you point of depression 2. Okay? So we talk about what's called a Huffman code. And And Huffman was a student at MIT in the 1950s, and he was taking a course on information theory, presumably. And the professor gave them a choice to take a final exam or to write something or other to some efficient algorithm for coding. So Huffman evidently didn't have time to study for the exam, so he wrote out some algorithm, which turns out to be one of those fundamental things in information theory. Okay? Grad student. That's what you guys are. And instead of doing important work like this, you're listening to me. And the other lecturers, for that matter. I don't set myself up any more than, okay? It's your fault. They could be doing something useful, right? And you set up this tool. I mean, yeah, it's all a plot of the deep state. I'm just saying. Anybody remember which one of these is mine? Sure? I can use either one of them. I suspect it's okay, but I was just asking. I don't actually want one. Okay. So what's the Huffman code? So what I want to do is I want to spin. So what do I want to code things? I'll tell you why I want to code things in a second. So what I want to do is again, information theory is based on transmission of a string, right? So what I want to do, I have a process, and I want to transmit the results of a process. The process, in this case, is my roulette wheel. I'm going to spin my roulette wheel many, many times. I'm going to record the outcome, and I'm going to send it to you guys. All right? I'm sending it to you guys, and I want to know how I can do that efficiently. That's what I want to know. How can I do that efficiently? I can send you the stuff, right? But I want to give each outcome a name or a code word, all right? I want to send strings of zeros and ones. That's okay with you, right? I want to give each one a code name in zeros and ones, and I want to transmit this code to you guys, and I want you to be able to decipher it, all right? Cool. And I'm going to use binary codes, as I said, just to be concrete. We don't have to do that. All right, so there are 8 possible outcomes for my roulette wheel. We've just gone through that. We need 8 symbols, therefore. And I want the code string to be short as possible on average, again. And I'd like to be able to decode this as it comes in, all right? So as it comes in, I want you to be able to call off 6, 4, 3, okay? Not to wait until the end, everything's transmitted, and then to go back and deal. We'll talk about that probably tomorrow. So, I need 8 symbols, so you would say, well, let me give you an example of a code which would not be very good. Let's take the code. The number 1 would be, or x1, right? 1 would be coded with a 0. Number 2 would be coded with a 1. 3, 0, 0. And as I've written it down, okay, that looks really great. But it wouldn't work because the outcome string, that is the coded strings that I send you, okay, for the outcomes 3, 4, 2, and 1, 3, 6 would both be the same. So it's not a very good code because you wouldn't know what you have narrowed it down. It wouldn't be certain things, but you wouldn't know what it is, so that's not very good. I don't want to have that. Okay, I want to preclude that sort of thing. So here's a guess. Just take the binary representation of the numbers, -1. Okay, that's easy, right? I have, 1 is 0, 0, 0, and 0, 0, 1, etc., and everything is fine. I don't have the problem I just had before. The average length of a code word is, shockingly enough, 3 characters, 3 bits, right? Count them, 1, 2, 3, right? So, therefore, the length of any code I send is n times 3 because everyone is 3, okay? So you say, well, that's pretty good. And I say, well, let me do better. Well, so what Huffman said was the following. He says, 1952, he said, let me sort the outcomes in increasing likelihood. All right, so here you go. 8, 7, 6, and 5 are 1 over 164, and on the line down the line to 1, which has probability half. Let me sort them in that order. Right? You don't mind me doing that. That's cool. And now let me look at starting from the lowest likelihood guys, let me group them. Okay? Let me group them, and I've done that over here. 8 and 7, I could have taken 8 and 6 or 8 and 5, It doesn't matter. If I have to make a choice, I'll make a choice. It doesn't matter. I'll get a different code. The code is not unique. Okay? but nonetheless, the procedure is fine. 8 and 7, I group them together. Each was probability 164. Together, they have a probability of one or the other of being 1 over 32, obviously, right? So that's cool. I do that for 6 and 5 as well. And I want to continue to do this. I want to resort them. I don't have to in this case. I want to resort them from lowest probability to highest probability, now looking at the compound guys, right, together. So it still is the case that 132 and 132 are the smallest values among all the probabilities. So I'm going to group those guys together. Okay, here we go. They're now grouped together to 1/16. But now I have, okay, we're okay? And now I have 1, 2, 3, 4, 5 possibilities, right? 2 of them are 1/16, and those are the smallest ones. These are the 2 guys I'm going to want to join together, and so on and so forth. I keep on reordering if I need to. Okay, to always start with I always have this procedure begin with the lowest probability guys. All right, I do this again and again until nothing else remains. So here this is where I did it actually. Okay, so in the end, I have probability 1, right? In the end, I have total probability 1. If you get a number other than 1 at the top, you screwed up, right? Assuming you've normalized your probability, right? So this is great. I have a tree. What do I do with a tree? So Huffman says, assign a 0 to the branches going to the left and a 1 to the branches going to the right, all right? And I follow a branch down to one of the values that I can possibly have, okay? And it's the string of branches, it's the numbers, the zeros or the ones, assigned to those branches, which lead to that leaf. This is what we call the leaf, all right? Which is the code for that number. So for example, the 1 has a single branch starting from the top, and so its code is just 1. All right? On the other hand, the 3, for example, is 0, 0, 1. Is that clear? Okay? You know, you can check it for yourselves. This doesn't have the probability. I can decode this as it comes in. Okay? This is so-called prefix code. I'm going to get back to what those things are tomorrow. Okay? These things, and I can write down a code like this, and this is what I get. This is the code words that I get. So, for example, the very low likelihood guys have longer strings than the high likelihood guys. So that's good, right? So, for example, the 7 is 0, 0, 0, 0, 0, 0, 1. Okay? So that's 5 zeros and a 1. And say, well, okay, but this seems worse than what I just showed you a second ago, where everything had 3 bits. Because now I got 6-bit guys, right? So this is obviously just stupid, right? On the other hand, these 6-bit guys are less likely than some of the shorter ones. So, you know, how well do I do? So I want to compute the average string length, my code, right? And when you do that, so what is that? That's capital L. I'm going to come back to this a little bit later. That's the sum of the probability of the outcome K times the length of the code word assigned to the outcome K. All right? I have 8 outcomes in this particular case, and when I sum up all this stuff, I get 2 bits. Okay? I remind you. Okay, so first of all, this is better than the first guess. All right? It's better than the first guess. Now, remember I asked you the question, suppose I'm thinking of a number between 1 and 8 with an a priori likelihood as given. What's the best strategy? And I suggested that this was the best strategy. Okay? Well, if you look at this picture, and you associate a yes answer with a 1 and a no answer with a 0, this is exactly the same as the Huffman. Okay? So, the Huffman code gives you the best strategy for guessing in yes-no questions, for guessing an outcome of a random process where the probability, a priori probabilities are known. That's a big where, okay? Where the a priori probabilities are known. I don't always know them, but if I do, this is what I want to do, okay? This is what I want to do. And more to the point, I don't know if I mentioned it or didn't. If you remember, I computed the Shannon entropy of this guy, right? And it was 2 bits. I computed the average length of the Huffman code. It was 2 bits, right? So now you are reasonably well advised to ask whether there's anything better, right? So I come up with some hokey example. I gave you some nice anecdote about a smart graduate student, all right? Told you it was fundamental. Proof by intimidation, right? Right? I mean, you guys aren't gonna, I've got a microphone. You guys don't, right? It's like Donald Trump. He can send out Twitter and 64 million people can sort of try to sound out the words, right? That's the people who read his Twitter account. I mean, they can't read the words, but they can, right? But they can sort of sound them out, and it doesn't really matter what he's saying anyway, right? It's good, bad. Where's my banana? Anyway, it's great. So now, fortunately, I'm a US citizen, because otherwise this would eventually get back, and I wouldn't be allowed back into the... But it's okay, because I'm white. So everything is fine. All right. So if we can strike that part of the thing, nonetheless, my paranoia is still there. Okay. But the natural question is, can we do better? Right? Can we do better? And I tell you, no, you can't do better, but you shouldn't believe me, right? You should say, no, if you want to make that claim, you better really put some teeth into that claim. And so I'm going to do a little more proof by intimidation. If I don't do worse, I'm actually prove it. All right? Proof by intimidation is saying that there's a theorem called the source coding theorem of Claude Chan in 1948. And he says that there's a lower limit on any encoding which doesn't lose information. All right? Which doesn't lose information. A lossless encoding. He says the lower limit is a lower bound, and he says the average code word length cannot be shorter than the Shannon entropy. All right? So if we believe the theorem, and I'm going to prove the theorem to you. All right? No, not today. I'm going to prove the theorem to you, so let's believe it. If we believe the theorem, then the Huffman code, right, has done as well as it possibly can, because it saturated the bound of the Shannon entropy. Okay? As did my guesses saturate the bound of the Shannon entropy. I can't do any better. Right? So there isn't any better strategy. There may be an equivalently good strategy, but there's no better strategy than the one I gave you. Okay? That's really, really remarkable. This is an amazing theorem. Okay? This theorem, because look at this. Okay? You guys think about entropy in statistical mechanical terms, in thermodynamic terms. Right? It's got real meaning, right? And over here, when you think about it like this, it's completely different, right? Doesn't it just blows your mind, no? The answer is yes. Right? It blows your mind. I mean, it's a completely different way of thinking about what entropy is. Right? It's a completely different way of thinking about entropy. If you want to send me information and you try to make it too short, and entropy is how short, it's going to get fuzzy. Okay? Shortest possible description has the length of the Shannon entropy. Remarkable. It's a major, major theorem in information theory, and we're going to prove it. Let me just give you a couple, just to have fun. I'll repeat this tomorrow, I suspect, because basically we're out of time now, right? So we're out of time. I love Donald Trump, and I want to make America great again. So so I've treated you guys like physicists. I've intimated that because of you have the same type of delinquent high school education that we have in Israel, that you don't know anything about anything other than physics and math, by showing you some pictures of art and insulting you along the way, right? Well, I didn't really. I was sort of trying to be nice after all, right? I have a 5-year visa, but still, I'm going to eventually close my way out of every country in the world. So I've shown you some artwork. Discussed simplicity, sorta. I try to intimate that order has some relation to the simplicity. Haven't demonstrated that, but sort of suggested it. Done a gambling problem. Told you how I cheated my daughter. Actually, I really didn't. Really, I didn't. This is on tape that I didn't. Okay. And now I'm going to give you some math, okay? And this is going to be, there's going to be some rigor here. So if you don't like math, that's just tough luck on you. But these are going to be real proofs, honest proofs, real, honest proofs, okay? Not physics proofs like, if it looks big, it must be infinite, all right? Chemical engineers, it's the joke about odd numbers, right? You know the joke about odd numbers. We'll make it about chemical engineers. Since we have an easy, right? We have a mathematician, a physicist, and a chemical engineer, right? And the mathematician, they're saying, let's see, 1's prime, 1's prime, 3's prime, 5's prime, 7's prime, 9's not prime. It's an exceptional case. 11's prime, 13's prime. All odd numbers are prime. Physicist says 1's prime, 3's prime, 5's prime, 7's prime. 9's not prime, experimental error. 11's prime, 13's prime, all odd numbers are prime. The chemical engineer says 1's prime, 3's prime, 5's prime, 7's prime, 9's prime, 11's prime, all odd numbers are prime. I don't know why I told that joke. It's the drugs. It's the drugs. Don't do drugs, guys. It's really not good. It's really not good. Or if you do the right kind. Or use them responsibly. Drink responsibly. I love the signs on the road here. If you're drunk, don't drive. If you're drunk, you can't read the sign. Are you drunk? You shouldn't be driving. All right, it's pretty good. But there you are. So okay, so in the -1 minute I have, definition. So I'm going to just show you what is the sign of things to come, right? A source code. I'm going to define source code. A source code, it's called the source coding theorem. So I'll tell you what a source code is. For a random variable, which I'll call x, is a mapping from the range of x, possible values that random variable can take, to this thing called d star, which is unnecessarily complicated, but it scares people, right? Which is a set of finite length strings of symbols of d letters. So I've used 2, right? I've used a binary alphabet, 0 and 1. But in principle, you could use 1, 2, 3, 4 if you like, and then d would be 4. Right? In principle, you could do it. There's no reason not to do it. So I'll be overly general here. All right? Then the notation is going to be that c of x. So x is the value of is one of the outcomes, one of the possible values that my random variable can take. C of x is the code word corresponding to x, and L of x is the length of that code word. Okay? Think about binary, it's easiest, right? So 0, 0, 0 has length 3, for example, trivially. And I gave an example here. Random variable, let's say, is the color of a pixel, which is red, green, blue. And I can give us a code just drawn from nowhere. The code for red will be 00, the code for green will be 10, the code for blue will be 11. In that case, my range is red, green, blue, and my alphabet is 0, 1. Okay, that's the source code. Okay, I've already given you examples of that. That's the source code. And I'm not gonna, and this is what's gonna be we'll start with tomorrow. Okay, so thank you very much. And now I gather that we have tutorial at some point where you can watch 3 lecturers try to pass off their questions to each other. I plan to pass all the questions off after me to those guys, so there's no real point in asking me any questions. Come